Uh, well, a very good evening, everyone. So today we'll start today's live session. So here is the today's live session 5. So we'll start from question number 1. We'll wait for 5 minutes if somebody will join. Hello there. So we'll start now solving the questions. The question number first is the direction of dislocation line is parallel to the Burgess vector in a dislocation of the type. So here you can see, here I am showing these two figures, figure A and figure B. Just a bit. Okay. So figure A and figure B. This one is figure A and this is figure B. First one is showing the edge dislocation. In that you can see this xi. This one is a line vector. Sorry, line vector, and this B. It's already written here. Sorry for that. It's line vector, and this B here, it is a Burgess vector. And as you can see here, both are perpendicular to each other. This plane and this one. Okay. So an edge dislocation, it is not possible. Mixed in edge itself is not possible, so mix also is not possible. What about the screw? Here you can see the screw one. Here it is a line vector, and this is the Burgess vector that is parallel to this line vector. So hence both are parallel. So the answer will be of this screw dislocation. Okay. Here two definitions are also given. This dislocation line and Burgess vector. What is that? So dislocation line means distance between the slip line and unslipped region, and Burgess vector is measure the magnitude of slip and displacement direction. And for your clarity, here you can see I have taken a curve surface. In that, this one is burst vector, that is called mix dislocation, that is having mix dislocation. This is screw dislocation, and this is edge dislocation. Okay, so like this, it will be having mixed dislocation together. If the surface is like this. Here, the question number 2 is the stacking arrangement of FCC crystal is. So as we have already discussed in previous slides, the first live session I have discussed about this in detail, FCC. HCP, CCP. All I have discussed in first live session. So, and that I already discussed how it works. Okay. I will take this atom as a red color. Suppose that is atom A. Then this three atom as a little yellowish color. This three atom as a greenish color. Then again this atom red color. So here you can see the stacking is like A, B. First one is A, then second one is B, then third one is C, then fourth one is again A. So it is a ABC type of stacking is available in FCC crystal structure. So this is very simple question. So the answer will be option number 1. Okay, so question number 3 is like the possible slip plane of BCC structure is. So here hint is there. One hint is here. Hint is slip planes are packed, closed planes. So closed packed planes are what? In BCC itself, we can see I'll just draw one cube. X, Y, Z. Here you can see 101 plane L. One zero plane also I'll draw here. Okay. 0.3. Okay. So according to this, the central atom is coming in both planes, and the possible flip plane will be both here. So answer will be option number 1 and option number 3 and option number 4. Both are possible here. Okay. So how many slip planes are possible in different cubic cells? Cubic. Okay, I'll just write down. In SCC, 6 number of slip planes are possible. So in SCC, 6 slip planes are possible. In BCC, BCC, 48 slip planes are possible. In that, only 12 are active. Okay. And FCC, there will be 12 slip planes possible. In HCP, there will be 3 slip planes are possible. Okay. So we'll move toward the next question. The next question is, what type of crystal structure is having maximum critical resolved shear stress value? So for that, we have a formula to calculate the critical resolved shear stress value. Formula is sigma sigma critical resolved shear stress is equal to cos phi cos lambda and this cos phi is depends this value angle thing depends on plane orientation, plane orientation, and for simple cubic it will be 0. So here the option won't be the fourth one, since this value will be this cos phi into cos lambda, the value will be 0, and they're asking for having maximum critical resolved shear stress value. So we'll move toward the further. So here the answer will be HCP, since the sigma CRHC will be the highest for this maximum. If you want to find out the theoretical shear stress value, that is very easy way. I'll show you the formula. Here it is written already, this formula. This formula says that this tau is directly proportional to B Burgess value. If it will increase, then the theoretical shear stress value also will increase. Sigma theoretical stress, shear stress value. And theoretically, the B value will be higher for SC, then BCC, then FCC, and HCP. Now, the next question number 5, which is what is the most favorable slip plane for FCC crystal structure? As you know, in FCC, this 1 1 1 plane is having ABC, ABC, kind of ABC kind of rearrangement. Hence, the answer will be most favorable slip plane for FCC crystal structure will be 1 1 1. It will go and this 1 1 2. What will happen is it will convert this ABC D, E, F, then again A, B, C, D, E. That's why the answer will be question number 3. So question number 6 is the energy associated with surface defect is the maximum for aluminium is due to, say, the twin boundary is a consequences of stacking fault. Okay, it is like twin boundary is the consequences of stacking fault. So it is not directly associated with the energy surface defect. Associated energy with surface defect. Okay, so here we can say directly. Here I am showing a one table, and that they have mentioned that the energy per unit area of intrinsic stacking fault and twin boundary for several FSC metals, the table. In that, it's you can see the stacking fault is given for the aluminum and platinum is very high, and based on that only we can correlate the answer, and the answer will be this option number 1, stacking fault. Okay, now question number 7. So question number 7 is the stored energy in a copper crystal due to the strain fields of dislocations is 12,000 kilojoule per meter cube. The dislocation density of copper is, they're asking dislocation density. Okay. Dislocation density of copper. Here they have given assume the shear modulus is equal to 48 GPa and Burgos vector is B is equal to 0.26 nanometer. As we know, they as here given things are like like one area. How we can calculate the how we can uh, separate the volume into area and area and uh, like suppose we have one volume, how we can divide into area and the height. So area will be this much and height we are increasing by stacking the layers of atoms. So here also this copper crystal is made up of like one area, particular area. On that so many layers are there. So it is increasing and it is forming this 3D volumetric uh, crystal. So the formula for this will be this one. We just have to put the value and we'll get the answer of the density. So strain energy per unit volume, EV we can write, and elastic strain energy per unit length. So whatever the unit length energy is there, how much we have? We have around, I'll just write a representation and dislocation density. So dislocation density is rho m. Okay. Here, how we can calculate this elastic strain energy per unit length? For that, it's given here already. Oh, sorry. This is volume. Per unit volume is 12,000 kilojoule per meter cube. It's given this meter cube it means that it is in volume. What about this energy unit length? So this is there. So that is around EL is equal to 1 by 2 GP square. So here you can see 1 by 2. Z value is what 0. Sorry 48 GPa into 0 0.26 square nanometer square into GPa. So we have to calculate into meter cube. We have to convert this value in meter cube and we have to put this value into this formula and this volume uh, energy per unit volume we have already given in meter cube, kilojoule per meter cube. For that we have to convert it into 12,000 into 10 to the power 3 joule per meter cube, and that's how we can calculate the rho m density, dislocation density of copper. Okay, so wherever we were, the rho. Rho we can calculate through EV upon EL. Okay, that's correct. Okay, so we'll move toward the next question. So that's how we can calculate this dislocation and density. So that will be around 7.39 into 10 to the power 15 meter per meter square. So question number 8 is copper has abscisic crystal structure. Copper has abscisic crystal structure if the lattice parameter A is equal to 0.36 nanometer. The length of the Burgers vector for the slip plane to operate is. So it is a straightforward question, and that what we have to do. Just we have here, I have already mentioned, already taken this X is a lattice crystal structure cube. In that lattice parameter, this A is 0.36 nanometer. Okay. So the length of the Burgos vector for the slip plane to operate is. So length of the Burgos vector we have to define. So for that, this plane we already know what is this plane. This is 1, 1, 1 plane, and this direction we know already, 1, 1, 1 plane, and direction will be 1, no, 1, 1, 0 direction. So the B will be 1/2 of 1, 1, 0, this direction. So in that, the half length of this length, that is called, not this one, sorry, from here to here, this length. So we know 1, 1, 1, 1, 1, 0, what will be there? It will be 4R, for FCC 4R is equal to root 2A, and that will be 2R, it means A by root 2. Okay, so the answer will be, we can find out through this, it will be 0.25 nm, nanometer. Here it is already simply defined how we can calculate this 4R value. Since from here to this distance, this place to this place, the distance is like 4R, that is around root 2. According to that, you can calculate. Now, question number 9. The tilt angle of a tilt boundary in BCC iron uh, A lattice parameter is equal to 0.287 nanometer with edge dislocations 750 nanometer apart is low angle tilt boundary. This is, you can assume how it is happening. So here you can see this place to this place, this density is, sorry, this distance is t. We have to calculate the distance of between these two. Angle, sorry, angle we have to calculate. We have given this as dislocation as 750 nanometer. And here is the formula that we can apply and we'll get the answer. So D already given, and this angle is theta that we have to calculate. Since it is a very low the value of this degree, this angle is very low. So we can directly put this value and this value. So we'll get the value of tilt angle. So the answer will be 0.02 degree. You can calculate and you can. One thing also for VCC and the B value is given here that you have to mention. Okay, for that, this instead of this formula, we have to keep this only. So we just have to keep this values here. So the answer will be sine theta by 2 is equal to d by 2 by d. And that's how we can calculate the tilt angle of the tilt boundary for basis. Yeah. Now the question number 10. At 750 degree, a solid has one vacancy for every 10 to the power 5 atoms. When the temperature is 900 degrees centigrade, this number is 1 in 10 to the power 4. The activation energy required to form a vacancy in the solid is in kilojoule per mole. Consider gas constant R is equal to 8.314 joule per Kelvin per mole. So we have given at 750 degree the vacancy is 1 in a 10 to the power 4, 5. If 900 degree, then 1 in a 10 to the power 4. As you can see, they are asking everything. The temperature is given in degree centigrade, but we have to convert since this rate constant, we can say it is in Kelvin. We have to convert these things into Kelvin. So it will be 1023 degree Kelvin conversion of this degree Celsius, and 900 it will be 1170 Kelvin. Okay. Now the formula is simply this one. Number of vacancy is equal to total number of atoms exponential of minus QV upon RT. So this temperature would be in Kelvin since R is in Kelvin. Total atom for first formula we can keep 1 is equal to 10 to the power 5 exp QV is equal to, we have to calculate, and R we have given already 8.314 into 1023. Another one value is equation 1 we can tell, and another one is 1 is equal to 10 to the power 4 exp QV upon 8.314 into 1173 Kelvin. Equation 2. We have to just divide equation 1 by equation 2, and you'll get the answer. That will be approximately option number 1. 1531 kilojoule per mole. Okay. Okay. So question number 11. The stored energy in a copper crystal due to strain field of dislocations is 14 megajoule per meter cube. The dislocation density is the magnitude of perfect Burgers vector of copper is 0.26 mm and the shear modulus of copper is 35 GPa, gigapascal. So this is we have already did for question number 7 similar. This dislocation density we have calculated rho. Go to question number 7 here. We have given the value of E volume, that is in 40 into 10 to the power 3, sorry, 10 to the power 6 joule per meter cube. A linear we have to calculate, which will be like 1 by 2 GB square. General formula is like this. We have to put the value of G, that is 35 gigapascal, and V 0.26. I think it won't be in mm, it will be in nanometer. We just cross check. Yeah, it should be in nanometer. So square, after converting the units, we'll get the value of E1 and we have to put this values into AV upon energy of volume dislocation energy, strain field of dislocation, that will be EV upon EL. Okay, and we are calculating rho n. So after calculation, we'll get the answer that will be approximately this one. Question number 1. It is in 10 to the power 6, not here. Okay. After that, the stored energy in copper crystal due to strain field of dislocation is 14 megajoule per meter cube. Sorry, why it's coming to that? I think something happened wrong. Okay, question number 12. I didn't put, I think, while I'm making PPT. So I'll just cross check this. And the last I will explain this question number 12. So we'll move toward the question number 13. After that, I will come to question number 12. So I'll just cross this one. Typo error. Okay, so question number 13. Question number 13 is a single crystal of copper is loaded under a stress state such as sigma 2 is equal to minus sigma 1, sigma 3 is equal to sigma tau 23 is equal to tau 31 is equal to tau 13 is equal to 0. Here 1 is equal to 100, 2 is equal to 010, and 3 is equal to 001. And the stress sigma 1 is equal to 6 kilopascal. What is the shear stress tau on the? So first we'll see here. These values are automatically came, so don't worry about this. Okay, so here in question this thing is missing. This will be equal to 0 that I have additionally added since this question was not uh, clarifying what is going on there. So I have just removed this as a clue. So the general formula is like this: tau x plus y is equal to this whole formula. Here this is containing shear stress also, but here as you can see there will be no shear stress. All will be equal to 0. We have to find out what we have to find out. We have to find out. I'll just show you here. This is the force direction. Okay, we can say force direction, whatever you will take, and this is the n direction, overloaded outward normal direction. That is, these are the values n for three different components, like three different slip systems, and d value is this one, that is called slip plane. D. So this is called slip direction, and this is called outward normal. Okay, so here what I had to calculate, we can calculate some values like I n x, I n y, I n z, I dx, I dy, I dz. This questions, the similar kind of questions we have done in the previous uh, live session as well. So this values how we can calculate. I'll calculate for this option number 1. Then later you can calculate for option number 2 and option number 3. Okay. So first I'll calculate for tau xx or 1. We can say tau 1 since this is the one x direction we have wrote as 1. So for that I will write here better I n x we have to calculate. I n x will be n value is given there 1 1 1 and x value is given 1 0 0. So n x will be 1 by root 3 I and y. It will be when different conditions are there, so I'll just write down. So n value is changing 1 1 1, and x, for x direction we will keep 1 0 0 generally. N value is here 1 1 1 again, and x y value is 0 1 0, I and y, that will be 1 by root 3. N is equal to 1 1 1, z is equal to 0 0 1. So I and z we can calculate again, that will be root 3. Okay, now what about this another value, that is day value. It's mentioned here. Mentioned here like day is equal to is equal to 1 0 1 bar minus 1 we can say, and x again we know 1 0 0, so I dx will be 1 by root 2, and d here it will be 1 1 bar 0, and y is equal to 1 0 1 0, and I d root 2. Okay, sorry, I dy I didn't check, I dy. Okay, the same function we have to take first to forward here, the same 0 1 0 bar we have today, and this value for that it will be 0, and on the last also id 0 1 bar, and it will be z 0 0 1, and the answer will be I d y is equal to minus 1 by root 2. Okay, so these values we have to keep on the formula, that is I n x I dx tau, sorry, sigma xx, we can say 1 also, plus I n y I dy sigma yy, and the sigma z here there will be no shear stress, so this value will be 0, and the sigma 3 value also will be 0 since it is written here. So we have to take only these two values for all three possibilities. So here we can write down 1 by root 2 root 3 into 1 by root 2 into sigma. Sigma is 6. sigma is stress that is already given, that is 6 kilopascal, and this value also not given. For x, oh sorry, this value will be minus sigma x is equal to sigma y minus sigma y. So, but here the issue is that is sigma I d pi is equal to 0. So we'll keep this whole value as a 0, and in the end we'll get root 6 into 6, that is equal to root 6. So this kind of option will be in the option number 1 only, but we can calculate for other two as well. Just we have to change this value, and value is same in the all three uh, given terms, and day value is also only changing. So here this values will change and we'll get the different values of direction cosine. The I is direction cosine. These things I should write. Now, to question number 14. A crystal of a crystal of aluminum contains 10 to the power 12 meter of dissociation per meter cube. Calculate the total amount of energy per meter cube associated with these two locations. Assume that half of the dislocations are edge and half are skills, and the B we have to calculate what would be temperature rise if all the energy could be released as heat. Data for aluminum atomic diameter is given there 0.286. I think it is a nanometer. Crystal structure FCC density 2.7 milligram per meter cube, atomic mass 27 gram per mole, specificity 0.9 joule per gram per centigrade, and shear modulus J is equal to 70 GPa. Poisson's ratio mu is equal to given here 0.3, and R is equal to also given R is equal to 0. Sorry, R is equal to 8.023 joule per Kelvin per mole. For calculation, there will be two formula. First, first we'll what is given here. We'll see atomic diameter D A is equal to 0.286 nanometer. As here they're asking to calculate the total amount of energy per meter cube associated with the dislocation. First, they are telling to assume that half of the dissociations are from edges and half are from screw. So edges will just write the row edges. It will be 1 by 2 10 to the power 12 per meter square. It is in density. And then another one is screw. That is 1 upon 2 10 to the power 12 meter square. Okay, 2 are there. Then what else is there? Epsilon E. This energy will be 1 upon 1 minus mu. Mu is a Poisson's ratio. ZB square on meter square. Sorry, 2 square. Sorry, 2 GB by 2. This is what H. Dislocation of energy for H. And what about dislocation energy of screw? It is simply 1 by 2 ZB square. So they are asking for energy in meter cube. So total energy will be E into rho E plus rho energy to rho energy. Okay, after getting G value we have already given, B value since it is a FCC crystal structure, so B value will be dA by root 2. And here we can calculate the B value, what is that is called Sears, oh sorry, Burgers vector. That value we can keep here in this two formula, and this value we can multiply with this, so total energy we can get. Okay, Okay, first here we can solve like this. And the option B, how we can solve for that, this total energy, whatever it will come, we have to keep as mcp delta T. And after that, we'll just calculate the total energy equal to in rho V Cp del T. And volume is already uh, density we have given here, specific heat also we have given here in centigrade, and so we can calculate this del T according to that. Okay, volume, it will go here, total energy upon volume. So this will be automatically it will convert into volume. Since this is in volume only, we are calculating energy per meter cube. It is in a volume itself, so we don't have to calculate the volume here. We don't have to keep volume here. General formula is like this. We need to write total. So we have converted into this. It is already containing the volume part, and rho we have given, Cp we have given. Just we have to divide, then we'll get the temperature difference. Based on that, we can calculate the temperature rise. So the option number first will be the correct here. Okay, so the next question is an abscissa monocrystal nickel is seared by assuming that the dislocation density is equal to 10 to the power 8 per centimeter square and it remains constant during deformation. What is the average distance each dislocation will move? If the shear strain rate is 10 to the power minus 4 per second, what is the mean velocity of the dislocation? The radius of nickel atom is 0.125 nanometer. So the average distance of each this location will move. We have to find out. For that, the formula is simply okay, here of you. So this is shear strain. We have given the rho value ten to the power 8 per centimeter cube, 10 centimeter square, and average distance L. We have to calculate. B. We can calculate using FCC. Uh, atomic diameter B is equal to A by root 2. So, and if we'll convert this one is 4R is equal to root 2A. 4R upon 2. Okay, this will be uh, 4, no 4, root 2A by 2, and we know A is equal to what? 4R by root 2, that we have to keep here. So B value will come as a 2R. Okay, that value we can keep here, and another value K. K is depends on varies from 0.1 to 1. So for mean value, like average distance, this each this location, I'm not sure what which value we can keep. So I'll uh, discuss in the next class what value we can keep there. And one more thing, this gamma values also have an issue. It's not proper mention what will be there. Okay. Then the next they're asking the mean velocity of the dislocation. For that the formula is simply like this. The shear strain rate is equal to rho dislocation density into B Burger square into V, that is called volume. That is called velocity, mean velocity. Sorry, this is mean velocity. So we have to calculate the mean velocity. For that, the formula I'll simplify. Just we have to put the values and we'll get the answer. The values are rho, rho is 10 to the power displacement density 10 to the power 8 into B. 0.25. How we calculate it? Using this form. Okay. And just we can calculate the mean velocity. And here will be here we will wind up the answer will be option number 1. Thank you so much for joining. The question number 6, it has some issue. I'll just cross check and I'll let you know in the next class. As well, this question number 12, it is mistakenly copied as a question number 11. That also I'll take care in next class. Thank you so much.